Once we estimate a coefficient, the next question is obvious. How much should we trust it? A point estimate by itself is never the end of the story, because every sample contains noise. Inference is the part of econometrics that tells us whether an estimated effect is precise, whether it looks statistically distinguishable from zero, and how much uncertainty surrounds it. In this episode, we are going to build the logic behind the tests, p-values, confidence intervals, and f-tests. The formulas matter, but the big goal is interpretation. We want to know what evidence the data actually give us and what they do not. Why do we need inference at all? Because an estimate is just one draw from a sampling process. If we took a different sample, we would usually get a different estimate. So inference asks whether the number we got is large relative to the sampling variation that naturally comes with estimation. This is why economists care about both the coefficient and the standard error. A coefficient can be economically large, but estimated very imprecisely. It can also be statistically significant and yet economically trivial. Inference gives us a language for separating signal from noise. To do inference, econometrics relies on a few key probability distributions. The normal distribution is the familiar benchmark. The chi-square distribution comes from sums of squared standard normal variables. The t-distribution appears when we standardize an estimate using an estimated rather than known error variance. And the f-distribution is what we use when we test several restrictions together. So even before hypothesis testing starts, the basic geometry of inference is already sitting inside these reference distributions. The t-distribution matters because in practice we do not know the true error variance. If a statistic were standardized using the true sigma, we would often get a normal distribution. But once sigma is replaced by sigma hat, the standardization itself becomes random. That is exactly what produces the t-statistic. Likewise, when we compare scaled chi-square variables, we get an f-distribution. One helpful fact is that as the degrees of freedom become large, the t-distribution gets closer and closer to the standard normal. So small samples and large samples behave differently, and inference has to reflect that. Under the normality assumption, plus the standard regression assumptions, OLS estimators are normally distributed conditional on the regressors. That is what allows exact small sample inference. But because sigma is unknown, we plug in sigma hat, and the test statistic becomes t-distributed instead. The difference between standard deviation and standard error is doing a lot of work here. Standard deviation uses the true population variance. Standard error uses an estimate built from the residuals. That is why inference is never just about the coefficient. It is always about the coefficient relative to estimated uncertainty. For a single coefficient, the test statistic is beta hat minus the null value, divided by the standard error of beta hat. If the null says the coefficient equals 0, then the numerator is just the estimate itself. Under the null, that statistic follows a t-distribution with n minus k minus 1 degrees of freedom. The basic idea is simple. If the statistic is too large in absolute value, the estimate is too far from the null to be explained by ordinary sampling variation alone. Then we reject the null. At that point, we have to decide what the alternative hypothesis actually is. A one-sided test asks whether the coefficient is specifically positive or specifically negative. A two-sided test asks whether it differs from the null in either direction. That choice matters because it changes the rejection region. In a one-sided positive test, all of the significance level goes into the right tail. In a two-sided test, we split the significance level across both tails. So the same estimate can look stronger or weaker depending on the economic question being asked. Suppose a regression output reports a two-sided p-value of 0.211 for a coefficient on training hours. If a negative effect is not economically sensible, a one-sided positive alternative may be more appropriate. In that case, the one-sided p-value is roughly half of the two-sided number, or about 0.106. That is much closer to the 10% level, though still not strong evidence by conventional standards. The lesson is not that we should manipulate the test after seeing the result. The lesson is that the alternative hypothesis should match the economic question before we interpret the output. P-values and confidence intervals are two common ways of summarizing the same underlying evidence. A p-value tells us, under the null, how likely it would be to observe a test statistic at least as extreme as the one we got. A confidence interval instead gives us a range of parameter values that remain plausible at a chosen confidence level. If 0 lies outside a 95% confidence interval, then a 5% two-sided test would reject the null of no effect. So these are not competing ideas. They are two reporting formats built on the same inferential logic. A confidence interval is usually written as the estimate plus or minus a critical value times the standard error. The estimate gives the center, and the standard error determines the width once we scale it by the appropriate t critical value. Wider intervals mean more uncertainty. Narrower intervals mean more precision. In practice, confidence intervals are often more informative than a bare significance label, because they show both where the estimate is and how much room there is around it. So far, we have tested one parameter at a time, but many economic questions are joint questions. We may want to know whether two coefficients are equal, whether several variables can be dropped together, or whether a whole block of regressors matters. Separate t-tests do not answer that correctly. For joint restrictions, we use an f-test. The unrestricted model lets all coefficients vary freely. The restricted model imposes the null hypothesis. Then we compare how much fit is lost when those restrictions are enforced. The F statistic is built from the change in residual sum of squares between the restricted and unrestricted models. The numerator measures how much worse the fit becomes when the restrictions are imposed, scaled by the number of restrictions. The denominator scales that by the unrestricted model's error variance. If the restrictions barely worsen fit, the statistic is small and the null looks plausible. If fit worsens sharply, the statistic is large and we reject the null. The same logic also shows up in the overall significance test reported by regression software. That overall f-test asks whether all slope coefficients are jointly 0. In other words, do the explanatory variables collectively help explain y? This is why the f statistic and r squared should be read together. A regression can have only modest fit and still be jointly statistically significant, or it can explain little of the total variation and still contain real signal. So the right question is not just how large r squared is. It is whether the regressors jointly improve our explanation of the outcome relative to a model with no slope terms at all. Inference gives econometrics its language of evidence. We moved from distributions to t-statistics to p-values and confidence intervals, and then to f-tests for joint restrictions. The next step is to put this inferential machinery inside the full multiple regression model, where omitted variable bias, partial effects, and interpretation all become more realistic and more demanding.